The sun's power, friend or foe? Imagine wielding the immense power of the sun, our most formidable natural force. Could we harness its energy for our benefit, or would meddling with such colossal might spell disaster? Solar Radiation Modification, SRM, is not just science fiction. It is an ambitious idea that merges innovation and unpredictability. On April 2, 2024, a groundbreaking solar radiation modification (SRM) test was discussed in detail. This important experiment, part of a growing field of climate engineering, aimed to assess the feasibility of using cloud-altering techniques to combat quote-unquote global warming. Before we get into a climate debate, today's video discusses how people are actively trying to reduce the Earth's temperature in the name of climate change. Depending on how you view things, this may seem like a noble cause or irresponsible. But let's understand what is actually going on before we jump to conclusions. It's important to note that Harvard researcher Frank Couch stopped exploring this type of research. Experts stated if implemented on a large scale could carry a wide array of unintended consequences according to Scientific American. Clearly, it's a very interesting debate. So let's jump into it. The SRM test involved the use of specialized ships that traversed predetermined oceanic routes. These ships were equipped with high-pressure nozzles designed to release fine seawater droplets into the air. The goal was to create denser, whiter clouds that could reflect more sunlight. The project was carried out under strictly controlled conditions, and its effects were monitored using advanced tracking and sensing technology. Satellites and sensors tracked the modified cloud formations, collected data on the distribution of the sprayed water droplets, and monitored changes in the cloud's reflectivity and the Earth's surface temperature. Why solar radiation modification matters to you? In our era of being told there's an escalating climate crisis, solar radiation modification, also known as SRM, emerges as a potential game-changer, offering a bold shortcut to mitigate global warming's relentless march. Yet, for every hopeful proponent, there's a cautious voice warning of the unknown risks and ethical dilemmas this audacious technology might unleash. As tech enthusiasts, we stand at the forefront of understanding this complex issue. Our passion for innovation extends far beyond the latest gadgets or apps. It's a drive to confront humanity's greatest challenges head-on in a responsible way. Unpacking solar radiation modification. Solar radiation modification could be considered as daring scientific endeavor or completely irresponsible aimed at reducing the amount of solar energy that reaches and warms the Earth's surface. The premise is strikingly simple yet profoundly ambitious. Enhance our planet's reflectivity, or reflective power, to bounce more sunlight back into space before it can contribute to global warming. The science underlying SRM is rooted in understanding Earth's intricate climate system and how it responds to fluctuations in solar radiation. Nature itself has provided compelling examples, like volcanic eruptions that have released vast quantities of aerosols into the stratosphere, temporarily cooling the planet through increased reflectivity. Ironically, after reading about this makes me think about science fiction plot from The Matrix, where humans decided to block out the sun to stop their war against machines, thus killing any solar power on the planet. I know it's just a movie, but hard ignore the visuals of a blacked-out planet. Scientists are exploring several ingenious methods are being explored to deploy SRM, each with its unique challenges and considerations. Stratospheric Aerosol Injection, SAI, involves dispersing reflective particles into the upper atmosphere, mimicking the cooling effect of volcanic eruptions. Marine Cloud Brightening, on the other hand, aims to increase the reflectivity of oceanic clouds by spraying seawater droplets into the air. At the heart of SRM lies the fusion of cutting-edge technology and scientific innovation. From developing specialized materials for aerosol injections to designing advanced dispersion techniques, technological breakthroughs are pivotal in transforming SRM from concept to reality. Conquering this challenge demands a multidisciplinary approach, seamlessly blending physics, chemistry, climatology, and engineering. SRM in the real world, from theory to practice. The transition from theoretical underpinnings to real-world applications of solar radiation modification, SRM, has yielded a series of captivating experiments and pilot projects worldwide. These initiatives are at the forefront of understanding how SRM might be safely and effectively implemented, offering invaluable insights into its potential impacts on our climate. One notable example is a recent experiment focused on stratospheric aerosol injection, SAI, where scientists released non-toxic materials into the stratosphere to study their dispersal patterns and reflectivity. This groundbreaking endeavor aimed to gather empirical data on how such particles could reflect sunlight away from Earth, with the findings offering promising insights into the feasibility of SAI as a climate intervention tool. Another compelling case study involves Marine Cloud Brightening, referred to as MCB, where researchers utilize specialized ships to spray fine seawater droplets into the air, aiming to enhance the reflectivity of marine clouds. Initial results have demonstrated that this method could potentially cool regions by increasing cloud albedo, though further research is crucial to fully understand its effects on local weather patterns and global climate dynamics. Driving this transition from theory to practice are remarkable technological innovations in materials science, atmospheric monitoring, and dispersion techniques. The development of more efficient and durable aerosol particles for SAI could reduce the need for frequent interventions, while advancements in satellite and sensor technologies enhance our ability to monitor and model SRM's effects on Earth's climate system with unprecedented precision. SRM Illustrated: Engaging Examples of Climate Engineering. The April 2nd test provided promising insights into the potential of MCB as a climate intervention tool. The test successfully demonstrated that the process could increase the albedo of marine clouds, thus reflecting more sunlight back into space. Initial data suggested that the altered clouds could potentially cool specific regions. However, the article also emphasized that the extent of surface cooling achieved was not yet sufficient to offset global warming on a large scale. Moreover, the effect of MCB on local weather patterns and overall global climate dynamics still needed further research. This could be just the start. Imagine a world where fleets of high-altitude balloons gracefully disperse microscopic reflective particles into the stratosphere, creating a celestial sunscreen for our planet. This is not a flight of fancy, but a vivid illustration of stratospheric aerosol injection, known as SAI, in action. Now, the alternative MCB approach, where ships traversing the world's oceans are equipped with specialized nozzles that release a fine mist of seawater droplets into the air, by reflecting just a fraction of sunlight back into space. This audacious method could significantly reduce global temperatures, echoing the cooling effects observed after colossal volcanic eruptions. The case against solar radiation modification. Long-term impacts and consequences. Opponents of solar radiation modification, SRM, voice a variety of concerns about the potential long-term impacts and consequences of this climate engineering technique. While SRM might offer a temporary solution to mitigate global warming, critics argue that it does not address the root causes of climate change, primarily our emissions of greenhouse gases. Breaking the natural balance. One of the key arguments against SRM is the potential disruption to Earth's natural climate system. Nature has a complex, finely tuned balance of processes and feedback loops that have evolved over millennia. By introducing a large-scale intervention like SRM, opponents argue that we could inadvertently unsettle this balance, causing potentially unpredictable and irreversible impacts on global weather patterns and ecosystems. Ozone layer depletion. Critics of stratospheric aerosol injection, SAI, a method of SRM, cite potential harm to the ozone layer as a significant concern. The aerosols introduced to the stratosphere could interact with ozone molecules, leading to a decrease in the ozone layer that shields us from harmful UV radiation. This possibility must be carefully evaluated before deploying such a strategy. Opponents also caution against what they term termination shock. If we became reliant on SRM to regulate global temperature and then abruptly stopped the process, the accumulated greenhouse gases could cause a rapid catastrophic rise in temperature, much faster than what we are currently experiencing. Another major concern is the uneven distribution of effects across the world. While SRM aims to cool the Earth globally, the impacts could vary significantly in different regions. These disparities could further exacerbate issues of climate justice and geopolitical tensions, as some areas might experience benefits while others suffer unintended adverse effects, such as altered rainfall patterns crucial for agriculture. Finally, some detractors argue that the promise of a technological fix to climate change presents a moral hazard. They fear that the prospect of SRM could reduce the urgency to cut greenhouse gas emissions, perpetuating a cycle of environmental degradation. In summary, while SRM presents an innovative approach to climate intervention, its potential long-term impacts and consequences are a subject of keen debate. The critics emphasize the need for comprehensive understanding, careful strategy, and transparent global dialogue to navigate this complex field responsibly. As we conclude our exploration of solar radiation modification, SRM, it's evident that this innovative approach to climate engineering holds both immense potential and significant challenges. Through this journey, we've demystified SRM, breaking down its complexities into understandable concepts and real-world applications that resonate with our tech-savvy sensibilities. The key takeaways are clear. SRM aims to cool the Earth by reflecting a portion of the sun's energy back into space. Methods like stratospheric aerosol injection, marine cloud brightening, and the use of reflective surfaces in urban areas exemplify the diverse strategies being investigated to achieve this ambitious goal. However, it's crucial to recognize that SRM is not a remedy for climate change. While it offers a potential pathway to temporarily reduce global temperatures, it does not address the root causes of climate change, such as greenhouse gas emissions or the Earth's natural cycles. It is important that ethical, environmental, and geopolitical considerations must also be meticulously weighed, as the impacts of SRM could vary significantly across different regions of the world, with permanent consequences. Looking ahead, the future of SRM hinges on continued research, technological breakthroughs, and robust international dialogue and cooperation. As tech enthusiasts and informed citizens, our engagement with this topic is very important. By staying informed and fostering open discussions about technologies like SRM and climate intervention strategies, we can contribute to a balanced understanding of its risks versus benefits, shaping a future where innovation and environmental stewardship could possibly coexist harmoniously. Let us know what you think in the comments below. Are we overblowing the climate agenda or underplaying it combined with altering how the sun interacts with the Earth? Let us know what you think below.